Okay, so anyway, um, it's not this. Let's go back to where we were. I hope you understand the difference now between addition and subtraction, right? So this, yeah, and why it works and why it doesn't. Okay, so we have this as our general solution. Now, from this general solution, we can kind of create as many particular solutions as we need, right? So part B, find the particular solution how that passes to the point 0, -4. So here's what we'll say: at the point 0, -4 colon, we plug it in and we get -4 equals plus or minus the square root of x squared plus c. And now we solve for c. And what do? We square both sides. Do we need to physically show that? No. As long as you're squaring it correctly. What is -4 squared? Positive 16, right? Yeah, positive 16. And when you square the right, the plus or minus goes away and you're left with x squared. Oops, I didn't plug in my x. That's why y'all are looking at me funny. There you go. 0 squared. Yeah, so now we get, we square both sides and we get the square root of c squared is c. So c equals 16, right? So now we plug it back in and we get y equals, leave a little space, the square root of x squared plus 16 under the radical. And now I have to commit deliberately to one solution, not two. I need to have a particular solution. It's either the positive or the negative. How do I know? 50-50. Yeah, you can plug your point back in and make sure you get the right value. When I plug in a 0 for x, I have to get out what type of 4? A -4. So when I plug in a 0, I get 0 plus 16. The square root of 16 is 4. In order to make it negative, I have to commit to the negative. So again, early on, they probably would have given you a positive y value. So the person who actually forgot and didn't even consider the negative would got it right, but not in today's day and age. So it's another example of the radical where you have to commit. Okay, so the Landon review tapes. I like that. I like that. Okay, shifting gears here now, and thank you, Miss T, for the alert there. It doesn't really happen on this campus very often at all. Yeah. So the law of exponential change. I think we studied this in pre-cal quite a bit, right? In pre-cal, we said that something grows exponentially if the more you have, the more you get, right? So anything that increases by a constant factor, like times 2 times 2 times 2 times 2, that's 2 to the x, that's exponential. Or something that increases by a constant percentage, right? Plus 50%, plus 50%, plus 50%. That would increase by 1.5. So that's all going to be exponential. So the rule is, though, the more you have, the more you get, because of this. The rate of change of whatever is growing or getting smaller exponentially, the rate of change of that quantity is directly proportional to the quantity itself. Okay, the more you have, the more you get. So if we write that mathematically, we could say if y is the quantity, then the rate of change of y with respect to t, time, is directly proportional to y itself. Hank. All right. So your dependent variables there and your dependent variables there. The more you have, the more you get. Right. Y changes faster when y is bigger. Directly proportional, right? What if y is small? Then the rate of change is small, right? What if I put in $1 at 5%? Is it growing very quickly? No. But what if I put in a big value here, like $1 million at 5%? Yeah, now it's growing faster because 5% of a bigger number is a big number, right? Than 5% of a smaller number. Now, here's what we want to do. If we truly understand that a situation is truly exponential, that it grows at a rate that's directly proportional to itself, we can skip the actual separation of variables and go right to the general solution. There are two of these that AP wants you to know. This is one of them, exponential, and the other one later on will be logistic. So let's go ahead and do this one time. Let's go ahead and separate and solve this general equation. It's with respect to t now instead of x. So I'm going to multiply both sides by dt, and I get k times y times dt. Does that separate the variables? It don't, right? I have a y on the left and I have a y on the right. So I'm going to divide both sides by y. I'm going to call it 1 over y dy equals k dt. Now, k is a constant. It's the constant of proportionality. Can it stay on the right-hand side with the independent variable t? Yeah, sure can. All right, so that would get the separation check. Now we can integrate both sides. And what would be the antiderivative of 1 over y with respect to y? Natural log of absolute value of y. Very good. Don't need the plus c. And then over here, what's the antiderivative of a constant with respect to t? A constant t. Good. K times t plus c. Very good. Very good. All right. Now we have to solve for y. So this is going to kind of look a lot like that first one I showed you where we went down the fork over here. And I said, don't leave plus c in the top. You're going to want to bring it out front. It's the same, kind of the same technique. Yeah. So how do I, first of all, peel back the natural log? What do I do both sides? E it, right? Now we don't have to show that. On the left, e to the natural log of blob is the blob. Now the absolute values is still there. And we get e to the kt plus c. Notice the c is now in the exponent. Now I can't drop the absolute values unless I put a plus or minus in the front. So I could say y equals plus or minus e to the kt plus c. And that would be acceptable for a general solution. But what's going to happen is you're going to have to then commit to whether it's plus or minus. And it's just not the version that we want. So I don't want to keep this as my general solution. So what's the little trick that we did on our first example today? E to the kt times e to the c. And since we are not committed yet to our final solution, e to the c can be called new and improved c, okay? And when you put new and improved c in the front, you don't need to put plus or minus anymore because ShamWow C, right? C itself, the sign of it comes out in the wash when you plug in a point. So this is the general solution. Yes, it sure is. This is the general solution to anything that's truly and particularly exponential, right? So you don't have to reinvent the wheel. This is one of the things College Board is expecting you to know. If you know a differential equation in that form, whether it's dp, it could be like dp dt equals k times p, right? dq dt, ooh, dq. That's what I like about Texas. What? Oh, does he? Oh, as long as the dependent variable's there, you can go right to the solution, right? And so here's the solution. It's the sect equation. The sect equation. That's how you can remember it. Y equals sect. The C, you get the soft C sound, right? The sect equation. C is an arbitrary value, right? So if you change it to n, I've seen this in some textbooks, kind of risque textbooks. They call it the naked equation. Yeah, it's naked, right? Oh man, he came out of the water and he was butt naked, right? So I don't know, sect and naked, it doesn't really matter to me. I just call it the sect equation. Y equals sect, y equals sect, y equals sect. Now C is going to be the initial amount. It's your y-intercept. That's what's interesting. If you remember from your exponential days, if you plugged in a 0 for t, you get C. All right, so this is going to pass to the point 0, comma C. C is then called the initial condition. It's the initial amount present. And by this, we mean the y-intercept of the graph. I say that right next to it, okay? K is your constant of proportionality. So here it is. Memorize, memorize, memorize. If dy dt equals k times y, then y equals sect. Y equals sect. Y equals sect. Okay? Now, y'all can remember that because sect kind of sounds a lot like sex, right? And if you replace it with n, you get the naked equation. So now you're talking about naked sex. And I don't know if you've seen any commercials during the Super Bowl, but there is a KY product that can be used towards, okay? So that's as much as I'm going to say. Yeah. But anyway, I don't know. I don't know if that textbook I was looking at, it was kind of trying to make, I don't know. But y'all are above that. I'm not necessarily above that. I'm kind of juvenile in my maturity level. But there you go. If dy dt equals k times y, then y equals sec. You can go right to the general solution. All right, let's look at some equations then that might apply. These show up nicely in free response questions. Suppose a population of bacteria in a particular culture went from 400 to 1600 in only 3 hours. Wow. Assuming that the bacteria population P grows according to this rate equation, dp dt equals k times P. This is where that bell in your head starts going off and you're like, what? I'm going to Taco Bell after school. No, ding, ding, ding. All right. This is going to be the solution curve. Instead of y, it's P, right? So P equals sect. There's the oops, sorry, the sect, it's E. I wrote it out phonetically. The KT is in the exponent, right? So you should recognize that. Where T is time in hours. Okay. So T is in hours, and then P is in bacteria. So we have units, right? My favorite units, bacteria. Find the value of K. Find the value of K. 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 K is right there. Point to it and go on to the next, right? Find K. I found it. There it is. I'm really good at hide and seek and search words. That's not what we're doing. Okay. We need to actually find the constant of proportionality. So here's what we could do. It went from 400 to 1600 in 3 hours. You can actually create two ordered pairs out of here. Did you know that? We don't know what time it started, but let's just say, hey, let's start our clock at t equals 0 when it was 400 bacteria. Then I can create another ordered pair. 3 hours later, it went to 1600, right? Now, all we have to do is plug in, okay? Now, if you're not really sure how to find C, you can actually plug it in first. We do know the value of C at this point, though, don't we? It should be 400. But let's say you don't know that. If you get that 0.0400, plug it in first at the 0.0400. Here's why. When you plug it in, you get 400 equals C e to the 0 times K is 0. And what's e to the 0? 1. So C equals 400. And now we can plug that in to the equation. So now we can know P equals 400 times e to the KT. Now you could have skipped that step and gone straight to, oh, C is the y-intercept. So I'm starting with this. And now we're going to plug in the other point at the point 3, 1600. This is a lot like, this is really pre-cal is what we're doing, or algebra 2. The only calculus that we did was recognizing that the differential equation had that form as its general solution, right? So 1600 equals 400 e to the k times 3, or 3 times k. And now I can solve for k. Yay. Divide both sides by 400. And what's 1600 divided by 400? 4. So you get 4 equals e to the 3k. And now I need to peel back the e layer. How do I peel back the e layer? Natural log both sides. So we get z natural log of 4 equals 3k. And now I have multiplication. How do I peel back the multiplication of 3? Divide by 3. So k equals the natural log of 4 over 3, or if you like, 1/3 natural log of 4. Now, this version is really nice. If this were a multiple choice question, that would be an answer choice in that form. Okay. Now, if it's a free response question, we could just stop right there. We don't even need to box it up. But I want to see if we can pick up on something here. I have this urge to box it. The 4 and the 3, that is vaguely familiar. If we come back up here, it went from 400 to 600. Let's see. That increased by what scale factor? 4. It increased by a factor of 4 in 3 hours. It quadrupled in 3 hours. Is the quadrupling 4? Is that where this 4 came from? Yes, because that's what happened when I divided 1600 by 400. So that 4 is your scale factor. And then is the 3 that the time it took to do that Is that the same as this 3? Or is that a coinky dink? It's not a coinky dink because that's that 3, which is this 3, which is this 3, which is that 3, which is that 3. That's the time to achieve the scale factor. So we can skip all of this algebra 2 gobbledygook in the future if we recognize it. So for instance, what if I gave you a question that said a population went from 50, let's say, a population went from 50 to 300 in 22 hours. What would K be? The natural log of 6 divided by 22. Yeah. Do you have to memorize that form? No, but it helps. Yeah, it helps. If you don't memorize that form, then you're going to have to do all this awesome, fun algebra 2 stuff, which it works. It works. And it is kind of nostalgic. All right. So anyway, there's so much we have to memorize in here. And a lot of it sinks in automatically from repetition, which we don't have the luxury of that. So keep that in mind. All right. Part B, how fast is the population increasing when the population is 3,000? How fast is the population of bacteria increasing? Is that a rate of change of population? Yeah, so I'm looking for dp/dt. That's my target. How fast is the population increasing when the population P is 3,000? This is almost like a related rates question, right? So I need to know what dp/dt is when P equals 3,000. Should I come back up here and plug my K value? Bless you. I could come up there and plug my K back in, right? If you wanted a working equation, you could say, so my population is 400 times E to the natural log of 4 over 3 times T. Here is my equation. So now, if you give me a T value, I can tell you what the population is. If you tell me what the population is, I can give you the T value. That's not what we're being asked down here, though, is it? I want the derivative. Do I need to reinvent the wheel and take the derivative of that all over again? No, I have the derivative form right there. So look, dp/dt, which is what I'm after, is K times P. Do I know what K is? It's the natural log of 4 over 3 times P. Wow. So I don't need to take the derivative. It's right here. And I have it in terms of P. Well, when P is 3,000, thanks for your help a little bit earlier. It kind of a little bit of a false alarm. When P equals 3,000, we get dp/dt equals the natural log of 4 over 3 times 3,000. Now, if this were a free response, you could stop numerically there, but you always then put units on it, which would be what? Leibniz notation is nice because it's the quotient. Units of population over units of time. What populations do we have? Bacteria. Yummy bacteria per hour. Now, because it's not a numeric interpretation, we can write it as bacteria/hour. You can also put PER there if you want to. Now, of course, that does simplify, right? 3,000 divided by 3. So if you want, you could put 1,000 natural log of 4 bacteria per hour. If you want to even get crazier, could you bring the 1,000 up as an exponent? Natural log of 4 to the 1,000th power bacteria per hour. Now that goes against everything the natural log is trying to accomplish, right? 4 to the 1,000th is huge. Logs are designed to make numbers smaller. So this is probably the best answer right here. Okay. Pretty cool. Pretty cool. Now notice how I plugged in. I said when P equals 3,000, that's fine. You could also say or dp/dt when P equals 3,000. You could do it like that with the evaluation bar. Either way, as long as you're signaling your intention, right? Like when you drive, you use your blinker, even when there's no one behind you. Notation, notation, notation. Yeah. Oh, absolutely. It's a reflex. I don't even think about it anymore. Right? Absolutely. It's like back when I used to drive stick shift, You don't even think about the clutch and the shift knob. You're driving, man. You're driving. All right. There's a little bit more to this, and again, on the one hand, I want to go fast so we can cover more. But on the second hand, I want y'all to thoroughly and totally understand it too. And so we'll finish on Monday. Your test tomorrow is not through any of chapter 5. No separable differential equations. It's just 4.1 through 4.4. Now, your free response, I looked at the test that I made last night. Your free response, I like this type of question. For your free response, where did it go? Man, this was a huge section, 4.4. Wow. Maybe it was 4.3. Hang on. Yeah, I think it was 4.3. Where did it go? I like this kind of question. Because I can ask you where F is increasing. Big F is increasing when big F prime, which is little f, is greater than 0. And I can even ask you for concavity by taking the second derivative, right? So the derivative of big F, it's going to be the function values, and the second derivative of big F is going to be F prime, okay? Yeah, I'm still recording. So let me just say this. Big F prime is equal to the y values of F, little f, and big F double prime, of course, are the slopes of little f, okay? So I might ask you, it's kind of like a throwback to concavity. Where is big F concave up? Well, big F would be concave up when the second derivative is positive. That's when the slopes of this graph are positive. Where are the slopes of this graph positive? From 0 to 2 and from 14 to 16. See that? Yeah. Where is big F increasing? Big F is increasing when big F prime is greater than 0. That's when the y values are positive. Where are the y values of this graph positive? From 0 to 9, 15 to 18. See that? All right. So that's the question that I came up with. I like it because it combines a little bit of chapter 3 back in there as a review. All right, I'm going to stop recording. This is recorded, so it'll be in the shared folder. Bye, everybody. Hey, don't smoke, don't do drugs, and don't fight, right? Just do what Michael Jackson said. Just beat it. Just beat it. No one wants to be defeated. Just beat it. Just be the bigger person, turn around and walk away.